All right, so let's talk about homework 5.5 when we're talking about our introduction to optimization. When we're optimizing, we're looking for either our minimum or our maximum. This homework is really just about writing the equations. You did not need to solve the problem. That's what's coming in our next unit. So if we talk about what is the smallest product of two numbers, our two numbers, I'm going to call my x and my y. Now what I want to do is get enough information about this so that I could rewrite one variable in terms of the other. So once I see that given that one number is exactly 7 greater than the other, I know that x is my larger number because he is equal to 7 more than my y. I'm looking to minimize my product, so I know that x times y is going to be equal to my product, and I'm looking for my smallest, so then I know that my product is going to be equal to, instead of writing x, I'm going to write 7 plus y times y, and that's what's going to be recognized as my equation. Now what's going to happen is, and here's what we need to understand, this is a positive quadratic, so it's going to be up like a cup, graph-wise. When we're talking about minimizing, we're going to find what point is the derivative equal to 0, the slope of the tangent line. So our next step is going to be to take the derivative, set it equal to 0, but we're not there yet. We're just writing the equation. Okay, next up. If the product of two numbers is 36, so x times y, or x and y are our two numbers, x times y is equal to 36. And the sum of the first number, I declared this one first, plus 4 times the second number is a minimum. So here is where I'm looking at my second equation, x plus 4y is equal to a minimum. I took my product equation and I rewrote it so that I have this value for x in terms of y. So what I'm going to do is I'm going to substitute this in for x, and I can say that 36 over y plus 4 times y is going to be my minimum. So this equation here is going to be what I'm going to use next to take the derivative and find where the derivative is equal to 0, because that will be the minimum of that graph. All right, next up, number 3, a rectangular pig pen uses 300 feet of fencing. It's built next to an existing wall. So this wall here is the wall of the barn, and I'm taking 300 feet and I'm I'm going to go ahead and make a pig pen. Only 3 sides of the fence are needed. I'm looking for my largest possible area, so I'm trying to maximize my area. My area I know is equal to length times width, and that has nothing to do with this wall. That area is still inside here, and this length times this width, that has nothing to do with that wall. But that wall has to do with my perimeter. So I know typically my perimeter is twice my width plus twice my length, but check it out, it's against the wall, so that means I only have one side for my length, and I know that my perimeter is 30 feet of fencing. So I go ahead and I solve for W, or solve for L in terms of W, and I'm going to go ahead and substitute that in. So I know that I have 300 minus 2W, which is the same as L, times my W, and this is going to be my equation that I'm going to then find the maximum. And take note, here my quadratic is negative, so I know my graph is down like a frown. So when I go to find the maximum, it'll be this point here that has a derivative, the slope of the tangent line, equal to 0. That's what's coming next. Number 4, what is the smallest perimeter? So I'm going to look for the minimum for a rectangle whose area is 16 square inches. So I know I have this rectangle, and I know that length times width is equal to 16. That's my one equation. I'm going to solve for one of my variables. Keep in mind, you could have solved for W in terms of L. I just happen to have solved for L in terms of W. I'm going to minimize my perimeter, which is twice my length plus twice my width. And I'm going to go ahead and substitute this expression for length in here. Notice now I have all W's. Perimeter is equal to 2 times 16 divided by W plus 2W. This is going to be the equation that I'm going to then take the derivative. I'm going to differentiate it in order to find that maximum or that minimum, whichever my optimal, whatever I'm asking for. Here it's a minimum because it's the smallest possible perimeter. All right, so this last one, number 5, find the point on the graph for this function that is closest to the point 0, 2. So remember, we're not doing the math, we're just setting it up. So here's what we need to think about. Whenever we're talking about this idea of being the closest, we're looking for our distance, and that is what we're trying to minimize. Minimal distance, okay? So our distance formula looks like this. If it's easier for you to rewrite it as this to the 1/2 power, because remember the distance is equal to the square root. Remember, distance comes from Pythagoras. So c squared is equal to a squared plus b squared. Here c is equal to the square root of the difference between your x's is your a. If we have a line segment, the distance between our x's is our a. The distance between our y's is our b. Our 2 coordinates are here. And this is what's interesting. This coordinate was given to us. And this is the graph of y is equal to 4 minus x squared. So it's a parabola, it's a quadratic that goes down. And any point on this quadratic has an input and an output, and that output value is that. So that's my way of rewriting this equation in terms of just x. So here's my first point, 0 and 2. And my second point is x and 4 minus x squared. So the difference between 0 and x is negative x squared is x squared. Plus, this is 2 minus 4 minus x squared squared. So 2 minus 4 is negative 2, minus the negative x squared is plus x squared. Remember, that's squared. And then don't forget, we're taking the square root, so this whole value here is to the 1/2 power. That's just my equation. Next step is differentiating that. That's next lesson. All right, here's a little review on position, velocity, and acceleration. The data table gives selected values for velocity in meters per minute of a particle moving along the x-axis. So at t is equal to 0 is the particle moving to the left or the right. Because its velocity is negative, it's moving left or down because my velocity is negative. Is there a time during the time interval, 0 to 12, when the particle is at rest? So yeah, this is going to happen twice because notice my velocity goes from being a negative value to a positive value and then back to being negative. So there's going to be twice when that velocity is equal to 0. That's when it's at rest. Velocity equals 0 when the particle's at rest. Use the data from the table to approximate the acceleration at t is equal to 4. So we're looking for the rate of change. Acceleration is equal to the rate of change of velocity with respect to time. So the rate of change, 5 minus 2, 6 minus 2, 3/4 meters per minute, because this is already given to us in meters per minute. So the rate of change is meters per minute per minute. All right, let's take a look at 7. A particle moves along the number line. So this is the graph of the position. It's moving to the left when my velocity is negative. Velocity is positive, velocity is 0, velocity is negative. So it's moving to the left or down from 2 to 4, and then again from 8 to 9. That's when I have a v sub t is negative. It's moving to the right when velocity in terms of time is positive. So that's from 0 to 2, and from, oh, I put 6 here. It would be 7 to 8 when my slope is positive. When is the particle standing still? It's at rest at this exact moment when it switches from a positive to a negative velocity, and it's standing still here where my slope on my tangent line is 0. All right, that's your homework. Check back for the video, for the notes. Come to class with questions.